Right, this video is a continuance from the last video, which discussed how a change in concentration will affect equilibrium. So students typically have a pretty easy time understanding which direction that equilibrium needs to shift when we're thinking about a chemical equilibrium reaction as a teeter-totter. But sometimes students struggle with understanding what actually happens to the concentrations of the reactants and products when we have that shift. So the Fuse School has this excellent video that has an animation of what happens. Definitely not something I could create on my PowerPoint. So I'm going to play the portion of the video that has to do with concentration, and then I will go through some examples on my PowerPoint. And I do recommend going back and watching this video either by watching this beginning section of my video or looking up the Fuse School on YouTube.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right.
And what you should have noticed there is we had extra A and B, so we created more C and D to balance it. So what happened was we shifted to the right, so everything on the left decreased in concentration, and the stuff on the right increased in concentration. So if we shift to the right, the stuff on the right-hand side is going to increase, the stuff on the left would decrease. Okay, in order to make C and D, we needed to use up A and B.
If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract stress.
So watch right now. Okay, we added more C and D. So what's going to happen? We're going to have to shift to the left. Now look what happens to the concentration of the reactants and what happens to the concentration of the products.
The system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure.
Okay, so we'll come back to pressure and volume relationships. Okay, so back to this same reaction between nitrogen and oxygen. So if more nitrogen is added, how will equilibrium shift to counteract the change? So we're going to be adding more to the left side. So if you guys are using your pen or your ruler, it'd be getting heavier, so to speak, on the left-hand side. And that would mean that equilibrium needs to shift to the right. Okay, so it's shifting to the right. Now, if we're shifting to the right, that means that we are trying to make more products. We're trying to get rid of the excess nitrogen that we just added in the reaction. Okay, so if the reaction is shifting to the right, typo here. Sorry about that. I don't want to start the whole recording over again. How is the concentration of nitrogen affected? Okay, so we're not talking about as we add more nitrogen. We're saying if equilibrium is shifting to the right, what is going to happen to the concentration of nitrogen? Well, if it's shifting to the right, we're making more products. In order to make more products, we need to use up our reactants. So what's going to happen is the concentration of nitrogen is going to go down. How is the concentration of oxygen affected? Well, again, we're shifting to the right, which means we're making more products. In order to make more products, we use up our reactants. So the concentration of oxygen would also be decreasing. And how is the concentration of nitrous oxide affected? Well, if we're shifting to the right, we're trying to make more products. We were trying to get rid of the extra stuff over here on this side of the reaction. So that would be increasing. Okay, so whichever direction the reaction is shifting, that side of the reaction will have the concentrations increasing, and the side that it's shifting away from is going to be decreasing. So we'll do one more example. Okay, so same reaction. Now, if oxygen is removed, how will equilibrium shift to counteract the change? So if we remove oxygen, if you're using your ruler or pen, it's getting lighter on the left-hand side. So it's going to need to shift to the left to make more of that. I have a feeling I have the same. Yep, same typo. Sorry. Here we go. How is the concentration of nitrogen affected? Well, if we are shifting to the left, that means that we are making more of the reactants. In order to make more of the reactants, we're using up the products. That's how we make more of these. So if it's shifting to the left, we're making more of this stuff over here, so the concentration of nitrogen would increase. How's the concentration of oxygen affected? Okay, again, we're not talking about in this moment when we remove oxygen. I'm saying once equilibrium is shifting to counteract the change, what's going to happen? Well, because we removed oxygen, now we're trying to replenish that, okay, by making more of those reactants. So the concentration of oxygen would increase. Okay. And how's the concentration of nitrous oxide affected? Well, we're shifting to the left, which means we're using up this stuff on this side of the reaction to make more of this, so it would be going down. Okay, so changes to pressure and volume. So if you go to the Fuse School YouTube video, which I will make sure that I upload that to my website, I'm not going to show it within this video. They explain changes to pressure and volume a little bit differently. Whatever you feel more comfortable with is what I want you to use. So I'm going to give you the way I remember this. But Okay, first of all, pressure and volume are only going to affect the gas, are only going to affect gaseous reactions. Okay, so notice here I've got A plus B, which are both gases, goes to C. So if we increase the pressure, it's going to shift to the side with the fewest moles of gas. So you are going to need to know how many moles of gas are on each side of the reaction. So remember that the coefficients represent the number of moles. Okay, so we have 1 mole and 1 mole. So that means we have a total of 2 moles on the reactant side. And we have 1 mole on the product side. Let me see if I can go ahead and just add that in there really quick. So we have 2 moles of gas on the reactant side and 1 mole of gas on the product side. It's be a little easier with the smartboard. Okay, so if we increase the pressure, then we're going to shift to the side with the fewest moles of gas. So if we're looking at this reaction right here and I say, how will equilibrium shift if I increase the pressure on the system? It's going to shift to the right, okay, because that's the side with the fewest moles of gas. Okay, volume is going to be the exact same thing. So, you know, from gas laws, that pressure and volume are inversely proportional, which means that anytime pressure increases, volume decreases, and vice versa. So again, if we decrease the volume, equilibrium is going to shift to the right because that's the side with the fewest moles of gas. If we decrease the pressure, it's going to shift to the side with the most moles of gas. So if I am looking at this reaction right here and I say, how will equilibrium shift if we decrease pressure on the system or if we increase the volume on the system? It's going to shift to the left because that's the side with more moles of gas. So the way that I've always remembered this, just a little trick, is when you are under more pressure, like in your life, you probably want to be around less people. When you're under less pressure, things are good, not so stressful, you maybe want to be around more people, okay, more in the mood to party. And then volume is just going to be the opposite. Anytime pressure increases, volume decreases. So I just think about it in terms of pressure. Okay, when I'm under more pressure, I want to be around less people. Okay, and the opposite of increasing pressure, or the same thing as increasing pressure, would be decreasing volume. When I'm under less pressure, I want to be around more people. Okay, so you're going to count the total number of moles of gas, gases only, on each side of the reaction. And that's going to tell you which side has more moles or less moles, so you can determine which direction the equilibrium will shift. Okay, and just like the examples I just previously gave, then you will have an increase or a decrease in the concentrations of the reactants or products. Okay, so if it's shifting to the left, everything on the left is going to be increasing. If it's shifting to the right, everything on the right is going to be increasing. All right, so let's do a few more examples. Okay, so when we are changing pressure and volume, you can think about the gases being in this closed system where we have maybe like a piston to change the pressure and the volume. Okay, so see here, we would have to increase pressure to make this go down. And if you increase that pressure and if you push this down, notice that there's less volume available. Okay, so we have a reaction between nitrogen and hydrogen to form ammonia. So the first thing we need to do if we're going to be dealing with gases is count the number of moles of gas on each side. So if you write down this example, I don't want to exit out of the slide again. Should be taking notes. We have a total of 1 plus 3, so that's 4 moles of gas on the reactant side. Okay, remember I'm counting the coefficients represents the number of moles. Okay, so 3 and 1. And then on the product side, I have 2 moles of gas. Okay, and notice all of these say that they're gases, so they all do count. Okay, so if we are going to increase the pressure on the system, remember I said that if we are under a lot of pressure, we probably want to be around less people. Okay, and in the last slide, you should have written down that if we increase the pressure, it's going to shift to the side with the fewest moles of gas. Okay, so we said we have 4 moles of gas on this side, we have 2 moles of gas on this side. So the side with the fewest moles of gas is here, okay, which is the right side of the reaction. So this reaction would shift to the right. Okay, and then the reaction occurs from left to right, decreasing the total number of gaseous molecules until equilibrium is reestablished, excuse me. So which molecule would end up with the highest concentration? So if we were to be increasing pressure, we said it would shift to the right. So ammonia would end up with the highest concentration. Okay, and you can see that here, right? We have more ammonia once we increase the pressure or decrease the volume, same thing. Okay. So an equilibrium reaction that has the same number of moles of gas on both sides will not be affected by a change in pressure. So in this example, we've got 1 plus 1 is 2 moles of gas on the reactants, and we have 2 moles of gas on the product side, which means they're equal. So if you increase the pressure or decrease the volume or decrease the pressure or increase the volume, there will be no change to equilibrium. So if you were asked that, the reaction would not shift, it would be no change. Okay. So how would you change the pressure of each of the following to increase the yield of products? Okay, so in this reaction, we would want to count up the number of moles of gas that we have on each side. So notice right here we have solid, so I have 0 moles on that side. Okay, this one's also a solid, so that wouldn't count. I have 1 mole of gas on the product side. So if we want to make more products, we would need it to shift to the side with the most moles of gas, because this side has the most moles of gas. So we would want to, oops, forgot I have the plan here. So when gases are present, a change in pressure will affect the concentration of the gas. If the pressure increases, the reaction will shift with the fewer moles of gas and vice versa. So carbon dioxide, again, is the only gas present. To increase its yield, we should decrease the pressure. So remember, we counted up the number of moles of gas on each side. We have 0 on this side, we have 1 on this side. Okay, the products, we wanted to increase the yield of products. We decided the products have the most moles of gas. So the situation where we'd want to be around more people was when we were under less pressure. Okay, or you can just memorize that if you increase the pressure, it's going to shift to the side with the most moles of gas. Okay, in this reaction, let's count the number of moles of gas on each side. So this is a solid, so that doesn't count. I've got 3 moles of gas on the reactant side, and I have just 1 mole of gas on the product side. So if we wanted to make more products, in this scenario, since I've got 3 on this side and 1 on this side, the products have the least moles of gas. So which situation would make us want to be around less people or shift to the side with less moles? Okay, so in this scenario, we'd want to increase the pressure to shift the reaction to the right. So there's kind of multiple levels of thinking here. You need to understand which direction equilibrium is going to shift, And depending on which side you want it to shift towards, you need to give it the appropriate conditions. Okay, if we're talking in terms of concentration, if I wanted to increase the concentration of products, we could, of course, we could go with the pressure volume, or we can go back to the other example where I said, okay, well, if we add more fluorine, it's going to shift to the right and make more products. Or I could say if we remove SF6, okay, it's going to shift to the right, and that would increase the yield of products. All right, in this example, I have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So there's equal number of moles of gas on both sides, therefore a change in volume will have no effect. And we will come back to the temperature changes on the next video.